And it's jolly hard to find out by reading the literature. And nobody really knows what these different forms of the different things actually do, except that, luckily, one or two groups have solved the structure. And they all have a catalytic purple subunit. They all have a scaffolding green subunit. And then these B subunits look completely different depending on the two that have been structurally solved. Quite different. I mean, there's no sequence homology and there's no structural homology either. Okay, so then the question came, which of these, or maybe all of them, is phosphatase X? So at this point, a summer student came to the lab and went through the same thing again. I mean, Satoru just cloned and sequenced all these wretched B time, all the ones he could find. And the bottom line was that B delta, so that's something that looks like that, was the one. I mean, I don't think there is any B alpha, beta, or gamma in a frog egg extract. It is all B delta, so that's the form. Okay, and that was good because none of the others showed any loss of activity. So it is B delta. And then we found that B delta was the same as a mutant in budding yeast called CDC55, and there was a Drosophila mutant in this subunit known as twins, which also caused a problem with getting through mitosis. So this was all very encouraging. It sounded like we were along the right lines. Good. So then you do the depletion in one of these extracts, and we were terribly, terribly pleased by what happened. Namely, the cell cycle got completely buggered up, as we say. And it gets modified in two ways. Number one, so there's the B delta. It's about 95% gone. The control extract enters mitosis after about an hour. The depleted extract is tremendously accelerated. So we completely misinterpreted this. I thought that we were dealing with the enzyme that dephosphorylated the bulk of CDC2 substrates at the end of mitosis. So that means that, well, we're not dephosphorylating because we've depleted phosphatase X, so it gets it much, much easier. You need only 40% as much CDK activity to get into mitosis, and you get there much more quickly because, there's no opposing phosphatase. So that explains this huge acceleration. And then, of course, once we get into M phase, we can never get out because we're missing the enzyme that gets you out of mitosis. Great. So we wrote this up for the EMBO journal, sent it in. The referees were very nice, but wanted, as they often do, one or two more controls. And it's a jolly good thing they did too. Because it turned out that the interpretation that I've offered you was completely wrong. And the reason why it's completely wrong is this. We already knew that something about the control, that if you inhibited CDC2 by adding a very specific protein inhibitor called P27, that itself caused the appearance of this phosphatase activity. So that, if you like, CDK works by directly or indirectly, I'll show you it's actually indirectly, inhibiting PP2A B55. So this was another way of forcing exit from mitosis without degrading cyclins. And that's what the referees wanted us to use as an assay. So did the assay, here's the buffer control, we're stuck in mitosis, force exit by adding the inhibitor of CDK1, whoosh, we come out, APC3 gets beautifully dephosphorylated. These CDK targets, this is an antibody that recognizes many mitotic phosphoproteins, they all get cleaned out. Then compare the control mock depleted extract, which comes out after half an hour, with the delta B55 delta depleted extract. And hell's bells, there's no difference. Ugh! Yuck! Oh dear, end of beautiful hypothesis. This can't be the enzyme that dephosphorylates the bulk because when you get rid of it, they all get out. So this is awful. And did some more experiments and found that there are some complicated, but we still don't really understand this actually. And one of the reasons why we don't understand it, it sort of raises a horrible ambiguity, and you realize that going back to CDC, WEE1 and its effect on that WEE1 itself is known to be inhibited by CDC2. WEE1 is turned off by phosphorylation. So here's another case where opposition between CDC2 and the phosphatase can affect, it's recursive, you know. And it's very difficult to disentangle effects on the control system of CDC2 from effects, you know, in other words, are we looking at CDC2 regulation or CDC2 action? Regulation, WEE1 gets phosphorylated and turned off, and CDK1 is here opposed by PP2AB delta. I mean, we haven't actually shown that, formally speaking, but that's almost certainly true from work done in yeast by Doug Kellogg. Or are we, as I've hinted before, you know, we're mostly looking at this, or maybe it's both. So this is the most unsatisfactory part of this seminar. I mean, I just don't know the answer, and we need more experiments to probe this sort of peculiar thing. But what about the regulation? Because if we knew what the regulation was all about, we would be in much better shape, I must say. So there are really only two hypotheses to explain the regulation. We know it depends on CDK phosphorylation. So either there is a CDK site on one of these subunits, probably the B subunit, and actually if you look at it, there is a very nice, juicy CDC2 site on the B subunit, which is pretty well conserved throughout evolution. So that was a likely possibility, except that when we looked to see whether it did get phosphorylated, it didn't seem to get phosphorylated, so that's irritating. And there's something called a phostag gel, which is a fairly new Japanese invention, which really allows you to see whether or not things get phosphorylated at all. And there was really no evidence to say that this did get phosphorylated. So we didn't really favor this hypothesis, which then sort of leaves us with a second model, which is, in the case of PP1, it's been known for a very long time that there's something called a phosphorylatable phosphatase inhibitor. It's actually, this is not to scale. Actually, in PP1, this is a very small protein that gets in the way. But just to, so, you know, there's some kind of inhibitor protein which is activated by phosphorylation. So two helpful clues then came along. I finally managed to persuade Satoru to do the boiled control. Probably most of you are too young to know about the boiled control, but when I was growing up, you always did the boiled control. If you thought you had an enzyme, you know, you boiled it because that would kill it, and if what normally ought to happen didn't happen, you were sort of happy that you had an enzyme and it was probably a protein because you boiled it and it went away. So in this case, the boiled control is to take the supernatant. So you boil a crude extract, you take the supernatant, and then you dilute the supernatant. You dilute the extract in this boiled supernatant. And the idea is you're looking for, you know, it might be molybdenum, or it might be a heat-stable protein, or it might be ATP, or it might be dibubbleomactase. You just don't know what it is. And when you did that, it turned out that you could do infinite dilutions, and you did not activate the phosphatase. So that there really was something rational. There was something there, and that became very helpful. The other clue was that it turned out that there was increasing evidence, first from Michael Goldberg and then from Anna Castro and David Glover, that there was a protein kinase in there that appeared to act like okadaic acid. It appeared to act by inhibiting PP2A. And this protein kinase beautifully was shown, it was first found in Drosophila, but it was shown to be necessary for xenoport oocytes to mature, and it's actually needed for extracts to stay in mitosis. So this is pretty spectacular. So the question then was, how does Great Wall work and what does it phosphorylate? And using that boiled supernatant, these are protein gels over here, don't worry about them. What Satoru found was that when he made extracts and added Great Wall to them, that's without Great Wall and added Great Wall, a very simple pattern emerged. We'd never seen anything like this before, and basically only two proteins, this one and this slightly smaller one, get phosphorylated. This is P32 incorporation into the boiled supernatant.